Welcome back. So this lecture is kind of summary of all the concepts that we've been looking at over the last several weeks. And once we understand the summary, then we will go on to topics that are slightly advanced. And then after that, perhaps after 2-3 lectures, we will start the second part of the series of these lectures, where we will look at various applications of some of the theories we have seen in the first part. So in that sense, the next several minutes, half an hour or so, we will just go through things that we have seen, and we started with various types of models and things like that, but the real technical accuracy or whatever precision, we started with ODEs. Ordinary differential equations are one of the best ways of modeling physical systems, and not that there are no other kinds of systems. It's just that basically probably these are the most difficult of the systems in terms of analyzing and things like that. So suppose if you have a purely discrete time or digital systems, then many of the questions around existence, uniqueness, and beyond stability are easier than ODEs, right? Then you have the most complex part of this ODEs, along with some kind of discrete nature, what we call as hybrid or impulsive systems, but they are much more difficult than what we are seeing in this course. And of course, then you also can talk about things like stochastic models and whatnot, and then that's really the most difficult thing that one can hope one can see in real world applications are hybrid systems that have randomness in many ways, right? I mean, external noise could be coming, some of the parameters could be random, some of the initial conditions could be random, and all kinds of randomness can occur. So in this particular course, we have therefore picked that model that's not the most difficult one, but at the same time it provides us sort of an introduction to these complex models, so to speak, right? So when we and then something like Newton's law, which is ubiquitous. I mean, it's almost everywhere in mechanical systems, and similar systems are there in electrical systems that depend on other fundamental laws like Kirchhoff's laws, Ohm's laws, and whatnot. And all these laws, there was an inherent assumption that basically somehow modeling rate of change of some quantity in terms of those quantities themselves is a nice way of doing it. And then Newton initiated that mathematics as well as physical modeling through Newton's laws, and so ODEs are quite a natural way of doing things, right? But of course, then the question becomes basically, how do we resolve with this model called ODE? The questions of solutions, questions of existence, questions of uniqueness, questions of stability, and so on and so forth. So we will essentially go through the summary of what we have been talking about. So the first part, we'll talk about existence and uniqueness. Then we will go on to boundedness and stability, followed by the famous Lyapunov function method. And seems like a slight variation of Lyapunov functions, but it's an independent result by itself in many ways and quite powerful. And then finally we will see the latest topic that we have covered is basically linear systems and how they are useful, the knowledge of linear systems that are useful in analyzing nonlinear systems. Okay, so by now we've been seeing this equation again and again, and we'll see it much more throughout the course. But we understand what this means. X is a vector, right? X1, X2, and so on and so forth. Perhaps since I chose to summarize these things, I might as well remind you, essentially, whenever we write x dot of t is equal to f of x of t with this initial condition, what we mean is essentially this: x1 of t is going to depend on, and I'm going to specialize this notation to two-dimensional, and you can imagine after that how it will look for multi-dimensional. Right? This is what we really mean. We mean a set of differential equations that are coupled, right? Sometimes the coupling goes in one way, sometimes there may not be any coupling, but when we put x dot equals ff, basically f of x, we assume that there's possibility of coupling in all directions. And same thing with initial conditions. So we'll be having as many initial conditions as possible. Okay, and intuitively, given an ordinary differential equation, you can have initial and final conditions. You can have some other condition in the middle and things like that. But in this particular course, we assume that the problems that we are interested are in controls and things like that. So typically, we kind of assume that we know initial condition and we want to go somewhere, and we are trying to control through some parameters, though this model does not include at this particular point. We want to take it somewhere, so we assume that all these are initial condition problems. So in reality, we are not just considering ODEs but initial condition problems. Okay, and then also we kind of justified why we picked first order vector differential equations, right? As an example, if we had say second order equation like this, then it's a matter of defining the so-called state space, right? And then write everything in terms of these new states. X1 dot is x dot is x2, so we'll get x1 dot is equal to x2, and x2 dot is x double dot, which is minus g of x, but x itself is x1, so minus g of x1. So that's why in many of the examples you may have seen that the first equation is always x1 dot is equal to x2. So they're all coming from this kind of second order equation. So this is one possible state space. Now just to complete this thing, we haven't seen such an example before, but I could have defined x1 as x plus x dot, x2 as x minus x dot, right? So x1, x2, therefore in this particular case is simply 1, 1, 1 minus 1 times x and x dot. Okay, so it is just a similar transform, and you can clearly see invertible. So there is a one-to-one correspondence between these two variables and these two variables. So you are essentially this is a coordinate change kind of a thing, right? Essentially in this particular case, perhaps you are expanding the 2D plane and probably rotating and things like that. So and this is perfectly valid, right? I mean, even in this particular case, if I have x1 dot is x dot plus x double dot, x dot is what is x dot? X dot is clearly in terms of x1 and x2, x1 minus x2 divided by 2, right? So x1 dot is x1 minus x2 divided by 2, and then x double dot happens to be g of x and g of and x itself is x1 plus x2 divided by 2, right? And then similarly equation will be there for x2 dot. Okay, x2 dot is x minus, so it's simply x1 minus x2 divided by 2 minus g of x1 plus x2 divided by 2, right? Why should one choose this over the other? It really depends on the specific problem, but it's just a demonstration that it is possible to take a second order equation and convert it into its state space. The canonical way of doing it is basically pick the x and x dot and so on and so forth, but there are other ways of doing it, right? One has to, and then this is a linear transformation. One can actually do a nonlinear transformation too. It doesn't have quite the simplicity of coordinated change, but it, in some sense it is, right? So, we understand where we are coming from when we actually pick this particular model. And one of the first things that we need to understand is, okay, fine, we defined a differential equation. We understand what is the derivative with respect to time in this particular case. What do we mean by solving an ordinary differential equation or finding a solution for this particular differential equation, and what it means to us? In reality, there's a physical world. We are trying to model trajectory of a particular variable. Trajectory here do not mean that something is moving necessarily, but in a figurative sense, basically there is some variable x1, x2, or x or x dot or whatever it is. They are changing in time, and then I want to find out how they are changing in time so that we can predict what happens to this particular system, right? I mean, this whole point of modeling is to predict. So in that sense, it's nice to know the relation between, let's say, the derivative of a particular variable, set of variables in a coupled manner through this function f to all the variables. So we have this nice relation, perhaps coming from something like Newton's law, or we discovered through painstakingly analyzing the data. However we do it, we have this model, right? But if we cannot solve this particular equation, and then we have the ability of predicting, and I don't necessarily mean do we have to have an explicit solution or not, but we should be able to understand what's happening with the solution, right? So, but before that, what is the solution? Can solution be any function, right? It can or does it have to be even function? So those are the questions will come, and then basically there are again multiple ways of doing it, and we picked kind of the simplest possible solution to go with for this particular course. Not that other notions are not important, it's just that as an introductory course on nonlinear systems, we pretty much assume many assumptions that are easy to handle, right? So we call x of t function to be a solution to this particular ordinary differential equation. First, it has to be continuously differentiable with respect to time, right? I mean, that's the dependent variable here, independent variable here, and also it satisfies the derivative condition that we have, the ODE condition. And of course, let's not forget the initial condition. So it has to, the function, when you substitute t equals 0, it should be satisfying the initial condition. And after that, the function should be differentiable, otherwise we can't even take the derivative. And when we take the derivative, and the left hand side has to be equal to some function applied on this same variable, right? So that we call as a solution. So in many cases, if you recall any of the examples, basically we may have a case where you can solve this x dot equals f of x for an arbitrary initial condition, but for a specific initial condition we won't know which one, and then that potentially can cause a lot of confusion from a mathematics perspective. In reality, we won't even know if a physical system will behave like that. Much more importantly, a lot of these things are quite important in the sense that if we don't know that there is a solution, then how can we ever use some numerical method and then trust the answers that are coming out, because numerical methods are kind of an approximation, and they don't have the issues of existence of solutions and things like that, because they are just a kind of step-by-step process. You keep adding and things like that, and then no question of existence or anything like that, or for that matter uniqueness, right? So we need to understand the fact that basically whether a solution exists. And one of the simplest things that one can conclude is, if the function f is continuous, we are guaranteed to have a solution, right? Unfortunately, this particular solution, it will be continuously differentiable, and it will satisfy the differential equation. It's just that we will have no idea whatsoever whether the solution is going to be valid. I mean, we can guarantee the solution existence for next couple of seconds or couple of meters. I mean, both space and time, we cannot guarantee anything about this, right? So that's the problem, and then we therefore start looking for other conditions, more restrictive conditions that can guarantee solutions that are better. And more importantly, F continuity does not eliminate the possibility of multiple solutions. Once again, I want to repeat this again and again. Basically, multiplicity of solutions is mostly a mathematical anomaly. In real world, we expect a particular system to behave in a unique manner. So we also would like to have uniqueness. So under what conditions, under what kind of models can we play with so that they guarantee unique? And that's where the one level more, you have something called continuity, and then basically on top of it, if we add something called Lipschitz continuity, in terms of the definition, it's you have some definition in terms of this Lipschitz constant. If we check, we get both continuity and the so-called Lipschitz continuity. We can guarantee uniqueness, but again, the solution happens to be quite local in terms of how much interval of existence is what it is called. For what interval of existence, either in the negative time or positive time, can we guarantee the solution? And when it comes to unique solutions, that's a nice thing. Basically, if you have also negative time, we don't have any, if you are at a particular point, you can predict where you're going, and you also can understand where you're coming from. If you have multiple solutions, then that may not be the case, right? Anyway, so it's nice to know that Lipschitz continuity gives you unique solutions and things like that, but there are stronger conditions, and those stronger conditions is one such condition is continuous differentiability with bounded derivative, right? If you have both of these things, then basically we are in a nice world. Basically, you have solution everywhere in space. And if f is continuously differentiable everywhere and uniformly bounded, then basically the solution will be exist everywhere and also for all time, right? Unless it blows up in the middle and things like that. So all these conditions are only sufficient but not necessary. So that means you can have any of these things not satisfied, but still you can have perfectly nice solution, right? So if in case you encounter some system where none of these things are satisfied, perhaps these are not necessary to show that there is a solution, and maybe for that particular system one may be able to show uniqueness and existence globally using a different method, or more direct method by actually demonstrating the solution. But no matter what, it's quite important to understand existence and uniqueness, as well as basically existence in the sense of whole time or certain time and things like that. All those things are quite important to analyze the system. We may not need to actually solve the solution every time, but need to know that there exists one for all time or for all space and things like that. Okay. And then once we have certain guarantees, then we can use numerical methods, simulations and things like that to perhaps demonstrate what is going on and things like that. And then in certain cases, it can actually help us design the control that we are looking for, right? So anyway, the summary of understanding these things is not so much basically we are interested in the the nitty-gritty details of mathematics, but from an application perspective, we need to see the consistency between the problem we are trying to solve versus what we expect out of this model, right? If somehow you believe that the physical system itself may have multiple solutions, it sheds some light into your model, whether that model can actually exhibit multiple solutions, right? I mean, it's probably not a realistic case. I'm just pointing that out. So one has to understand your physical model, physical system quite well in terms of what is the expected behavior of the quantity that you're modeling, x of t typically, let's say. So, and the differential equation that we associate with this particular variable, therefore, should satisfy those properties that are consistent with your expectation, right? So that's the key message as far as this particular existence and uniqueness. So one has to be knowledgeable about various conditions to understand and see if the physical model, physical system and the mathematical model you chose are consistent with one another, right? Now that we kind of understand solutions and their existence, so and from this point onwards, we assume that those are not an issue. Basically, there is going to be an ordinary differential equation model for a physical system, and we have a solution. A solution that can start anywhere in the space or restricted depending on the specific case, and then of course the solution will march to infinity. Now, I want to make this particular note. Basically, most of the results that we talk about are going towards infinity, but in reality, that infinity could be just 20 seconds, right? Yeah, I mean, if we could state something in an ideal situation, then in practical cases, it can be amended a little bit to understand that. So that brings us to basically understanding boundedness, right? So how, what do we mean by bounded? Basically, let's say I have this particular system. I may start somewhere and I may wander off and then basically come here, but I never go off to infinity, right? That's essentially boundedness. So of course the bound typically depends on where you start and things like that, but beyond that it's very simple concept in terms of understanding what is boundedness. Okay, so for now we are going to assume that it admits. So unique solution, as I already indicated, that's going to be a standing assumption throughout. The system is bounded if for every initial condition x of t is bounded, and the bound could depend on that initial condition. So one of the nicest things about bounded solutions is, intuitively speaking, let's go back to a picture here. So I know that let's say wherever I start, let's say I can conclude that this particular solution is bounded. So I can basically imagine some solution like this, right? Or maybe something like this. Okay. So no matter what, basically you can clearly see that you will have some limit points, right? I mean, you cannot go off somewhere, and you're kind of restricted to this bounded space, and therefore you have no choice but to basically either keep visiting the same point again and again, or one single point, right? So that means you can have limit points. What are limit points? If you have a sequence where it ends, let's say you have a sequence like 1 minus 1, 1 minus 1, and so on and so forth. What are the limit points of that particular sequence? Plus 1 and minus 1, because it keeps visiting that very often, and then it has two limit points. And this is an extreme example where it's not even a limit point, it's actually the point of the sequence. But you can imagine basically something like 1 plus half, 1 minus 1 plus half, 1 plus 1/3, minus 1 plus 1/3, and so on. Imagine a sequence like that. Basically, I can clearly see, as the next term is 1/4, and so on and so forth, 1 plus 1/4, and so on. It will eventually oscillate between two numbers, 1 and minus 1. So this any sequence, or in this particular case we have an orbit, if it keeps getting closer and closer to a particular point, we call that as a limit point, and then those limit points could be multiple or a single point depending on the case. For each trajectory it could be a different behavior and things like that. So those limit points, we call them as positive limit set. Okay, positive limit set, here the positive indicates that we are marching forward in time. One can imagine negative in time, and then we call them as negative limit sets. And what can we say about these positive limit sets? If the solution happens to be bounded, then the nice thing is non-empty. We kind of convince ourselves we have no way, nowhere to go but just to limit in one of these points, or more than one of these points, right? So it's certainly non-empty. Okay. And then we have something called compact. In simple spaces, there are abstract spaces where compact can be quite painful to define, but basically we understand these things as closed and bounded. Bounded is obvious. We are talking about a bounded solution, so therefore the limit points better be bounded. Closed simply means all the if there is a sequence of points that you build out of the limit points, it's a little bit confusing. So you have this limit set, positive limit set, and then you take bunch of a sequence of those limit points. Basically, the limiting of that particular sequence will remain. And why is it important? Sometimes it does get quite important to show. If you start within that particular set, you will remain, and then the limit points also is going to be within that set, can be used to show quite useful asymptotic properties, right? So, but for the time being, one can ignore this, but it's nice to know that it is closed. And just to shed particular more insight into this, closed comes from the fact that basically our solutions are continuous. Okay. So can you not have a closed nature in the case of discrete system? That's not the case. It will still use some kind of continuity assumption on part of something else, but there could be cases where you may not have closed limit set, positive limit set. You could have actually slightly different, and then we can throw away at that particular point, but something else could be true about those kinds of systems, right? So non-empty, compact. And then the other thing is connected, right? The connected is fairly intuitive. What it says is basically, if you have something like this, you cannot have two islands of limit points without any connection between these two in terms of the same trajectory. I mean, if this trajectory, since it is continuous, it will converge to one connected component of the space. If it is indeed going to two different things, then there will be a bunch of limit points in the middle, right? So this is kind of obvious, and again, if you think about discrete systems, connectedness will not come. But the last and most important thing is invariant, and this is the most technical part of the result about bounded trajectories. So invariant means if you start within that positive limit set. So, we start at some point initial condition, and we end up, let's say, this. Let me use a different color. Let's say this is the red color is basically what the set of limit points is. Now I'm going to do an experiment again. I'm going to start off within the limit set, the red curve. I'm going to remain within the red set. Right? I'm not going to spill out, right? The fact that it is closed, compact, invariant, and things like that, that's a very powerful result. And it depends on continuity, it depends on so-called semi-group property. Essentially, that says that if I start somewhere and go, say, 10 seconds, I can think of that as going 5 seconds and then starting again at 5 seconds and go for 5 more seconds. Along with that, you have continuity, and both of these things put together can be shown, can be used to show invariance of the positive limit set. And this, like I said, this is the most important property that comes to our rescue to understand these positive limit sets most of the time, right? So that's a very, very technical result that's quite useful for us. Okay, and and we call the system itself is convergent. I mean, because here we are not talking about any equilibrium points or anything like that. We are talking about system itself. When I say system, all the solutions, right? The system is convergent if for every initial condition x of t converges to a limit point, right? Not some kind of bunch of limit points, but one single limit point, right? If every initial condition will lead to some convergent point, then that we call that system convergent. And again, using the similar properties that we defined for solutions or so-called flow, if you recall, basically one can show that such a limit point will be equilibrium, and in certain cases one can show that those equilibrium points will have even better behavior, what we will see as stability, right? We have seen Lyapunov stability earlier, so such convergence will happen to only Lyapunov stable equilibrium points in certain cases, right? I mean, it's possible that this point is in such a way that from one side you will have convergence, and from the other side you may have divergence, and then we won't call such equilibrium points as Lyapunov stable, but typically it's expected that such convergence will happen to Lyapunov stable equilibria. So in general, a bounded solution may converge to a limit point or bunch of limit points, which we typically call them as limit cycle. That limit cycle could have an equilibrium point or not have, or bunch of equilibrium points, one finite number or multiple of the continuum of equilibria, depending on the dynamics of the system. Anything can happen, right? So you know, what's possible is basically you have this, let me go back to the picture. So it's possible that basically you start here, I end up with an equilibrium point. On the other hand, I can start here and then basically end up in some kind of limiting behavior where this particular circle may actually contain a bunch of equilibrium points, one single equilibrium point. All kinds of cases are possible. Now, the only other phenomena not possible in 2D, but you know, the famous butterfly attractor, for example, happens in 3-dimensional, basically where things will you know, look something like this, but it doesn't look as organized as a single orbit or something like that, but actually it keeps going back and forth, and then it covers the entire space, and they're called strange attractors. This is also an attractor. Okay, it's not as strange, but you can have strange attractors, right? And then the strange attractors happen when basically there is some kind of sensitivity to initial conditions and things like that. So this is kind of the behavior of any bounded solution, and you know, while we are trying to control systems, the best behavior that we can hope for is basically convergence, and you know, limiting to some particular point. Of course, if that is not the case, so at least we want to bound them to a certain small set or something like that, and then so the worst we can hope for is basically just get boundedness, right?